Okay, so hidden Markov models. So we have been discussing what are hidden Markov models. So we saw these are, um, we derived this equation last time, right? Oh, let me share my full screen so that you can see other things as well. Okay, you can see my screen.
Yes, sir.
Okay.
Yes.
So this is what we were discussing yesterday, that we have our phoneme sequences going like this, and we model it as a first order Markov chain, which means my current state, um, or basically my probability of next state is completely determined if I know my current state, right? Probability of or probability distribution of next states is completely determined if I know my current state. Conditional independence property. So using that, we kind of decomposed or used chain rule and then conditional independence property to write it like this. So my probability of S naught, you see S naught, I start from here. This is independent. Now probability of X naught given S naught, then probability of S1 given S naught, probability of X1 given S1, like that. And we see there are two categories of outputs. One output is the next state, the states, and one output are the visible parameters, visible acoustic parameters, for example, MFCC features or spectral parameters, spectral features. So that we call as X. So we say my transition between states, we call it as transition probability, and my emission of spectral parameters, we call it as emission probability. So transition probabilities and emission probabilities. So that's what we were discussing. So this is our hidden Markov model joint distribution. So we have initial state Z1, which is just the initial state, and you can have it as a one hot vector. For example, I will start with a silence state, for example, or it could be, you can define it anyway. Next, you have transitions, and then you have emissions, right? So that we discussed. Now, can you generate new data? Yes, sampling is easy. You sample along the chain starting from the Z1. You find out probability of Z1, you just sample it. And then X1 will be, this distribution is determined once you know Z1. And then you move on from Z1 to Z2. And then, so basically in this way, you can generate new data. And
Excuse me, sir.
yeah,
Sir, what is the meaning of generation of new data? I am not getting this.
good point. Good question. So it means, uh, given a chain, can I generate? So in your ASR, in your automatic speech recognition systems, you are more concerned about recognizing what is being spoken, like speech recognition. You are not generating new speech. You are just recognizing the available speech. Whatever speech is given, you are recognizing what is the corresponding sequence of phonemes or sequence of words, right? So you are not using generation. But imagine now another situation where you have text to speech model. Text is given and you want to generate speech out of it. So even there you can use hidden Markov models. It can generate speech for you, right?
Okay, sir.
Yeah. So generating new data, it will generate new audio waveforms. So yeah, in this course, I don't think we will be discussing about speech synthesis. We'll be mostly discussing only speech recognition. Okay, so this is basically generation that you are given.
Here generation means, can we say that the translation from one parameter to other parameter, from one domain to another domain?
Yeah, yeah. You have the latent domain or the text domain, and you have the audio domain. And recognition means going from audio to text. Generation means going from text to audio.
Okay, sir. Okay, sir.
Then now this is the problem which you will be dealing with. If you get a new observation xn, the audio, can you infer the corresponding state? And if yes, then you can use HMMs for classification. So we want this task. We want to infer what is my Zn given the observation, the audio features xn. And so there are, you might have gone through this inference part. It's a decoding process where I think here you can see the exact picture. At every time instant, three states are possible. For example, there are three phonemes, maybe silence and ah and oo. Three phonemes are there. Then at every time instant, you can have one of these three phonemes, but then these paths have some constraints. These paths, like from here, you can go to here with maybe higher probability, from here to here with a lower probability, here to here with a zero probability, let us say. So it means very, very restricted paths are there. How do you, so these restrictions also make your decoding easy, right? Because certain paths are eliminated automatically. So your decoding becomes easier. So this is, I think, the sum and substance of decoding, that you have the states and the jumps, like from this state, how much probability is there to go to this state? From this state, how much probability is there to go to this state? This is defined by the hidden Markov, by the first order Markov property. The probability distributions are conditioned only on single variable, like the my next state is defined only by the current state. So this is represented here by the transition probabilities between three states. And then this is a Gaussian mixture model, let us say, or a deep neural network, whichever classifier you want to use. And then this is the whole trellis, which shows what is the path you take when your time is increasing. So, and then you use Viterbi algorithm. That's it. Left to right HMM. So you basically have to now HMM, in HMMs you have to put the constraints, what jumps are possible. So for example, if you exactly know what is your sequence of phonemes, Hari, like I speak Hari and I also tell you I'm speaking Hari, but you don't know exactly how much time I spent at her, how much time I spent at how much time I spent at ra and at e and in the silence. So you can still use HMMs. You know that this is my sequence. Your path is constrained, but how much time I'm spending here, this is not known. So you can still, you can use HMMs and use decoding that you want to go from here to here, when basically this whole during this whole utterance I'm going from this state, this state, this state, this state, this state, this state until here. So my path is known, but exactly my trellis, how much time I'm spending, that is not known. So you can use Viterbi decoding to achieve this. So that's what you studied. Then in estimating the parameters, you studied how to estimate the parameters of a new hidden Markov model, where you do not know transition probabilities, you do not know emission probabilities. How do you estimate them from the data? Data means audio plus um, the sequence of phonemes, not even the exact time, but just the sequence. So from the sequence, you know the constraint path. Then you use decoding to find out what is the best trellis. That's it. So this is all about hidden Markov models. I think we can stop here. You have any questions, you can ask. Otherwise, I will start with the problem which I wanted to discuss in the last class. So this was the problem that, so here the same problem, you know the observations, your x at all the times, and you know the path, but you don't know how much time you have spent in each node or in each state. You have some initial estimate of probability of stay, but you don't know exactly what is the uh, like along these 10 days journey, how much time did I spend in each city. That is not known. So anybody has any question? Anybody has any question here? No questions? Okay. Then let's try to solve this problem. Let me use my notebook. Okay. So let's try to examine this problem. So you have, okay, 10 days. So one thing is clear, that I have to make a trellis of 10 days. And what is there in the trellis? There are three states: city 1, city 2, city 3. So city 1, just a minute. City 1, city 2, and city 3. And there are 10 days. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So first I have to draw the trellis, right? Where the x-axis is the number of days and the y-axis is the different states. So these are different days. The 10th day, 9th day, 8th day, 7th day, 6th day, 5, 4, 3, 2, and 1. And then these are the cities: city 1, city 2, city 3. And I know I'm starting from city 1, right? So I'm starting from city 1, I'm starting from here, and I'm ending in city 3. I'm ending here. This is fixed, right? Now, how do I make my path? So there are probabilities, probability of being healthy. So on this, at this time, he is healthy. The prisoner is healthy, 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 healthy. And then on the 5th day, he's sick. 6th day again, sick. Then healthy, healthy. Then sick, then healthy. Right? Now, what do I do? Yes, who would like to tell? What should I do now?
We'll find the transition probability.
Yes, yes. So we have to find the transition probabilities. So my probability of stay in city 1, probability of stay is equal to 0.8. Oh, I think I should have made this bracket here. Probability of stay is 0.8, not probability of stay equal to. Okay, I think small mistake there. Probability of, so in city 1, probability of stay is equal to 0.8. Now see, multiplication is a very difficult job. You have to keep multiplying 0.8 multiplied by 0.8 multiplied by 0.6 multiplied by 0.7. That the number will become smaller and smaller and smaller, right? Let's say there are 10 things. So if I have 0.8 to the power 10, how much is this? I have to open my Python to know how much is the value. Let us open Python. Just I'm using it as a calculator. So I have to say import numpy as, this is just a calculator. Even if you don't know Python, don't worry. Numpy is just a mathematical library. I will say np.power 0.8 comma 10. So 0.8 to the power 10, how much is this? 0.1. And if I have 0.7 to the power 10, it's 0.02 or 0.3. These are very small numbers. And if I have even smaller numbers, sometimes 0.1 will come. So it becomes really small, and it is difficult to track. So what we generally do, we convert them into log. And then, log probabilities you can add, like multiplication probability terms. If you take a log, then it becomes a sum of all log probability terms. So we say, what is the log of 0.8? np dot log 0.8. It's minus 0.22. So probability of stay becomes so basically the log of this number is equal to log of 8. It is minus 0.22. And what is the probability of move? What is probability of move that it makes the transition? What is that?
0.2.
0.2.
Yeah, 0.2. So it is minus 1.61. To make my things simpler, I will just keep it for the first place of decimal. Then city 2. What is the probability of stay? Log 0.6. It is minus 0.5. And probability of move, how much? Log 0.4. So minus 0.9. Then come to city 3. Probability of stay is how much? 0.7, which is minus 0.3, let us say. It could be 4 also. It's just we are approximating things. So, and probability of move is
0.3.
0.3, so which is minus 1.2. Okay. So far so good. Now remember what we have to compute. Where is my problem? We have to compute
How many days?
The term which we have to compute, the total probability is product of these different probabilities, right? Where it is? Yeah, this one or this one. So we have to multiply them. So if I convert log, then the log terms can just be added, right? So I have to maximize my log probability, or I see every term is negative here. So I can also take negative log likelihood, and I can minimize my negative log likelihood. right? So maximizing P implies this implies you are maximizing log P. This implies you are minimizing minus log P. Right? So if I just take negative values, I will say minus of log. This becomes plus. And I want to minimize the accumulated sum. You remember yesterday's problem where we were maximizing my sum across the field. Now I have to minimize my sum across the field. Okay. So what type of terms are there? Transition probabilities like this. And then we have emission probabilities. What are emission probabilities? So in city 1, we have probability of healthy, because healthy and sick, these are the two states which I'm observing. So what is my probability of healthy in the city 1? Answer is minus log of 0.7, and we have computed somewhere. This 0.3?
0.3.
And for sick, it will be 1.2. Okay. Similarly, this is probability of healthy in city 2 is minus log 0.2. We computed it somewhere. Minus log 0.2 will be how much?
0.6.
1.6. And for sick, it will be 0.2. Similarly, in city 3, probability of healthy will be minus log probability of healthy will be equal to how much? This is 0.6. So it was here 0.5, right? This value. And probability of sick will be how much? 0.9. Am I correct? Did I make any mistake? Did I make any mistake here? See, if we make a mistake here, then our entire trellis will be incorrect. So make sure that these values are correct. I will just verify from my solution. So this is here. Probability of healthy for city 1. Oh, there seems to be some mistake here. Oh, this is to the base 2. This is computed to the base 2. We have computed to the base 10. So it's all right. Whichever base you take, it's all right. So anyways, we cannot use this then. Yeah, tell me then what is these values are correct, right? We can say 0.5 is here, 0.5 is here. Yes, this is correct. I think it should be all right. Means like, okay, I'm unnecessarily trying to compare is not good. Okay, now let's come here. Now let's start computing the probabilities. So we have to start our token passing algorithm or the beta decoding algorithm. So our tokens are here in the beginning, right? My initial state is determined that we are here only. So there is no pi term, no initial probability term. Initial probability is 1 for this state. Now what do we do next? We have to make a transition. And where we can make transition, it says from city 1, I can either stay here or I can move to city 2. So right, or either I can either move here or I can move here. So now if I move here, what is the probability I accrue? Probability of move is 1.6. No, probability of stay is 0.2. So I get 0.2 score, and here I get 0.6 score, right? And then once I am here, I have to emit a healthy state. From here, if I emit a healthy state, in city 1, emitting a healthy state is 0.3. And then emitting a sick state is 1.2. Anyways, we are emitting healthy state only, so we leave it as 0.3. We can also say here it is also 0.3, but that is constant for all the paths, so we may ignore it also. But anyways, we can, to be more, so, so what we have to compute is probability of healthy given city 1 into probability of healthy given city 2, or probability of city 1 given city 1 into probability of healthy given city 1. Right, this is what these three terms I have mentioned here, this, and this. And since these are in log things, so we have to add them up. So what is my sum? So until here my sum was 0.3, but if I reach here, my sum will be 0.3 plus 0.2 plus 0.3, which is 0.8. And if I come here, okay, what is my probability of healthy in city 2? It is 1.6. So what is my sum here? 0.3 plus 0.6 plus 1.6, which is 2.5.
2.5. Yes, sir.
Thank you. Okay, now let's move on. I have got 2 tokens here. Now we move on to the next thing. If I stay here, I get 0.2. If I move here to here, I get 0.6. And if I stay here, I get how much? City 2 stays 0.5. 0.5. And if I come from here to here, how much was it?
0.6.
1.6, sorry. And since this is a healthy state, now what will be my emission here? 0.3 only. And if I'm here, my emission will be 1.6 only. Now you see there is a conflict. 2 paths cannot reach, so only one path will be taken. Whichever has the maximum, or in this case, the minimum score, yeah, that path will be taken. So this is 0.8 plus 0.6, 1.4, and this is something 3. So this path will not be chosen. Right? So I will not choose this path. I will choose this path. So I will.
Sir, could you repeat?
So here I have a conflict. That to reach this state, there are 2 possible paths, and I have to choose the optimal path, which one has the least sum, this accumulated cost, least cost. So the least path. So if I come from here, it will be 1.8, sorry, 0.8 plus 0.6, which is 1.4. And if I come from here to here, it is 2.5 plus 0.5, which is 3. So of course I will choose the least cost. So I ignored this path, I chose this path. So my sum here will be 0.8 plus 0.6, 1.4, plus the emission of this, which will be 3, right?
Sir, but they are both independent events, no, sir. So generally, when we take the probability, we add them. Right?
Yes, good observation. We are not here finding out the total probability to reach here. We are finding the best path to reach here. Our goal is to find the best path. The goal of Viterbi algorithm is to find the best single path. Multiple paths are not required.
Sir, then we can ignore the 0.5 even before we do it, because on day 2 we know that the maximum likelihood is that the people will be in city 1.
Yeah, but as you are going along, it may turn out that this path may turn out to be the best. If you remember the yesterday's problem, let me show
Yes, sir.
Yes, sir.
this problem.
Yes,
So
sir.
you can say here that here, no, not here. Here, 59 was the best. But as you moved on, this no longer remained the best. And even I think somebody asked a question also.
Yes, sir. From 19 to 1. Yes, sir. Yes.
124,
Yes,
124
sir.
was the best. If you have to stop here, then 124 is the best. But if you move on, then these gains are so low that this is not the best path, but this is the best path. So the goal of Viterbi algorithm is to find the best path.
So here we are ignoring the path with 0.5 because irrespective of how we, because we reach city 2 on, assuming we reach city 2 on day 3, the best path is through day 2 city 1.
Yeah, basically to reach this state means if I tell you that on day 3 you are in city 2, what is the best path to be in this state? Then you will say this is the best path.
Yes, yes. Thank you.
Tell me, sir.
Yeah.
Sir, here we are not moving from state 2 to state 1 because in question it is not going from to
Yes.
city 2.
Yeah. So
Okay.
that path is not allowed. So like going
Yes,
from
yes.
this to this is not allowed because
Okay,
our
sir.
path is constrained. That is the benefit of using constrained paths, that your trellis becomes easier, computations reduce.
Okay, sir.
Okay. Now let's come to this point. So here, what is the accumulated score? There's only one path, so we'll just add them. So it is 1.3. Right. Similarly, you can carry on. You can do the whole process, and you will attain one best path. Do I need to complete it, or is it all right? Okay. So let us say if I want from here, I can also go here. So if I go here, what is the transition probability? It is city2 move 1.0.9. What is the emission probability for city 3 to be healthy? 0.5. What is my accumulated score to reach this state? My score is 2.5
2.9.
plus 9 plus 3.9. So that's it. Now we move on to the next. This transition will cost me 0.2.
Sir, I have a doubt. Can I ask?
Yeah, sure.
Sir, in the because we are taking the negative log, that's why we are taking the minimum.
Yeah.
Suppose someone taking direct the probability, we are not taking the log or negative log. So we have to take the maximum path, no? Maximum value path.
Yes. And you have to multiply. You cannot add them. You have to multiply.
Yeah, we have to multiply.
That will be much more computationally difficult. Difficult means you have to keep track of all decimal places. So there are 10 decimal numbers, or in this case 20 something, 19 decimal numbers multiplying. So
Mm,
it will be very small number.
okay. Thank you.
Okay, so let's see. Next we have now to reach here it's very simple. 1.3 plus this 1.8. But to come here again, there is a conflict. Which path shall we choose? So of course 3 plus 0.5 is 3.5, and this is much smaller. So we'll choose this path. Then emission here for a healthy state will be again 1.6. So how much is the total? 1.3 plus 1.6 plus 0.6. So this is 2.9 and 3.5, right? So, and I will not choose this one. Okay, then you move on from here. To reach here, there are two possible paths, this one or this one. Which one shall we take? This path costs me 0.9. This path costs me how much? Let us check. In city 3, probability of stay is 0.3. Now, and also the emission of a healthy state from city 3, 0.5. Now tell me which path shall be taken? This is 3.9, this is 4.2. So definitely I will take this path and not this path, right? 3.9 and plus 0.5. So this becomes 4.4, right? Okay. In this way, you can complete the trellis. It will take me some time to complete. 0.2. This is 0.5, this is 0.3, and this is 0.6, this is 0.9. Now find out the best path. This is of course single path. So, okay, again emission here. This is a sick state now. Probability of sick in city 1, 1.2. Probability of sick in city 2 is 0.2. Probability of sick in city 3 is 0.9. So now which path shall be taken? Here, of course, single path. So we'll choose this. This is how much? 2 and 3.2. This is how much you have got. 1.8 plus 0.6 is plus point. Okay, so we have to find the best path. This is 4, and this is still the best path, looks like, right? So we take this path, 2.6, right?
Yes, sir.
0.6. And to reach here,
Sir,
yeah,
may I have a doubt?
sure.
Is it necessary to calculate our values at city 3 if we know that we haven't reached city 2 in any of the previous on any of the previous days?
Yeah, good question. Very good question. So there are two. No, yeah. So ideally, we should compute because, of course, in this case, somehow find that this path is not getting accepted at all. But there may be situations when you actually are reaching. So, for example, in your previous problem, which you studied here, so even if you know that this path was not this, or maybe somewhere, this was not the best one, this was the best, but still you computed and carried on with this, hoping that maybe in future it may become the best path, and it really became the best path, right? So in this case, no state can be ignored. Even this state cannot be ignored. Means there might be some path, and means no path can be ignored, I think. So yes, but there are situations when some paths can be ignored, like in this case, it could be ignored. And so, uh, so if we ignore this, this may cause errors, but the probability of those errors is very, very small. So in real practice, when there are, here we have only 3 states, let's say when there are 50 states or 100 states, right? There are 100 states. Then some such remote paths are ignored. It's called lattice pruning or the trellis pruning. You prune certain paths, like you know that certain paths are really not possible. So you just prune them, or you just don't compute those paths to save computations. But that may lead to errors, but it is very unlikely that it will lead to errors. Okay, so it's an approximation to save our computational time.
Yes, thank you.
Thank you. You will see this in full-fledged speech recognition. In it's called pruning, trellis pruning, or lattice pruning, or path pruning. You're pruning certain branches or certain paths when they are too low in probability, or which are so remote. Okay, now let's come to this part. So you have got, where are we? Okay, now we have to compute. I think you can do it on your own. And okay, I will just tell you from the solutions what is the path you will obtain. You will attain this path. Ultimately, your path will be this. You will stay here, this. So no, for 4 days only you stay here. This is not. From here you will move to this, and then you move here, then here. No, made a mistake again. So you stay 2 times here and then move on to the third one. Then you move to the third one. And you stay here for next 4 days and you end here. This will be your best path when you compute the entire thing. So you see the finally, whichever is the least score. Oh no, sorry. We have to don't have to look at the least score. We have to reach this state. So from this, whichever path reaches this state finally is the final path. Even if this is the least score, but you're not ending in city 1. You're ending in city 3. So this path is taken, and you trace back the path and you get your path. Okay. So then pardon.
Here we can say that if you enter once in city 3, then we need not to calculate the transition from 3 to 2. Am I right?
Yeah, 3 to 2 is not required.
Yes, sir. If once we have entered in city 3.
No, but you don't know when you are entering city 3, because you don't know this will be your final path. Could be you might have reached from here to here. Who knows?
Yes, sir. Up to 7 after 7 days, we need not to calculate the for 8th day. We need not to calculate the transition from city 3 to city 2.
City 3 to city 2 we are never calculating,
Okay, sir.
because city 3 to city 2 is not possible.
Yes, sir.
2 to 3 is possible. Okay. Now the next question is update the model using this observation with the single best path EM algorithm. So basically, you find out the single best path and use this path to update your model parameters. And redraw the following diagram with updated parameters. How will you do that? How will you re-estimate the parameters? Now, if you know this path, this is your single best path. Now you have to maximize the model probability using this path. How will you do that? So it's very simple. If you have read it, to update the probabilities, you will say, when you are here, what is your probability of city 2 given city 1? Probability of city 2 given city 1. This is your probability of city. This is the probability of stay for probability of move for city 1. So you have to find out how many times you were in city 1. So you were in city 1, 1, 2, 3, 4 times. And how many times city 2 was the next state? So only one time. So 1 upon 5 or 1 upon 4. What is the probability of stay in city 1? So this is basically probability of city 1 given city 1. So when you are in city 1 state, what is the probability that the next state is city 1? So you are in city 1 4 times. How many times is the next state city 1? So 1, 3 times. 3 upon 4. Right? Then next is probability of probability of move in city 2 is probability of city 3 given city 2. Right? How much is this? How many times are you in city 2? You are just 2 times you are there in city 2. Out of these 2 times, one is move, one is stay. So it is half. And similarly, probability of stay will also be half. Similarly, for city 3, probability of move for city 3 will be equal to how much? Oh, you're not moving here at all, but you are moving to the jail. So 1, 2, 3, and 4. So 1 upon 4. Because you move to the jail, the end position. And the stay will be 1 upon 3, 3 upon 4. So in this way, you have updated your transition probabilities. Now, what about the emission probabilities? So if you are here, how many times are you healthy? If you are in city 1, you're always healthy. 4. So probability of healthy is 1. Probability of healthy given city 1 is 1. Similarly, sick will be 0. Probability of healthy in city 2 is in city 2, you're always sick. Probability of healthy is 0. Sick is 1. Probability of healthy in city 3. In city 3, you are healthy.
मुझे से दुश्मनों की वजह से फंसी रहती है सब तुम्हारी होती है सब हाँ लेकिन वो बेचारी अंदर फंसी तो सिर्फ तुम्हारी वजह से सिर्फ तुम्हारी उसकी आवाज सुन के भी तुमने अपसेट कर दिया उसकी आवाज सुन के भी
Okay, so that's it. This is how we move, we re-estimate our parameters, as you can see here. Yeah. Any questions here? Any questions here?
No, sir.
Okay, if this is done, then next we will be, so we have completed our HMM portion. I would request that watch the videos properly, and also if you want to read more about it, I have given a reference on HMMs, which is in PRML book, Pattern Recognition and Machine Learning book by Christopher Bishop. In that book, I have mentioned the chapter and the sections which you can read. And also I have told you about CALD toolkit. If you read the documentation of CALD toolkit, there you will find how they have implemented hidden Markov models. That will be very useful for you. Okay. So let us say CALD Dsr documentation. I asked you to go through the tutorial for dummies, maybe to start with. You can very easily now make sense of what is happening here. Acoustic data, task, language data. It's just so basically now here we are creating the sequence of states. If each state is a phone, then whenever the label is 5, then you know this is that I am covering 3 states in this order. I don't know how much time I'm spending in each state, but these are my order of states, sequence of states. And then create 3 scripts. I think when you go through this, you will get to know the details. Feature extraction means basically just you have your audio files and you are extracting, in this case, MFCC features. And then you have your, what else? Training step, where you are training your HMMs, and then decoding step, where you are doing the bit-to-bit decoding. And graph is what we created, the trellis, basically, you can say. Graph is your trellis, the possible path which you can take. And for computational ease, so Kaldi makes a graph which is computationally easy to traverse. And then decoding means when you get your actual audio file or the audio features, you do the decoding over that graph or the trellis. And then yeah, alignment. And so yeah,
I have a doubt regarding LPC features.
okay, we can take it. Just a minute, let me just complete this part. I think, yeah, this is complete. Then you have to run .sh script, I think that's it. So basically, then your output, the decoded sequence is written in one of these files, maybe this file. That's it. So they have 2 kinds of models. One is the monophone model, mono alignment, and then triphone model. I discussed with you what is triphone model. Like each phoneme is influenced by the neighboring phonemes. So your state is not a phoneme now, your state is a triphone. Basically, my which is preceded by a g followed by a p, something like that. So each phone is like divided into multiple phones, or each phone could be of multiple kinds, depending on what was your previous and the next phone. That is called triphone. Okay, so I think we will discuss it further, but let me